Okay, in today's lecture, we're going to cover the section 1.2 material on row reduction and something called echelon forms for a matrix. And in this section, we're going to make a little more precise our method or our algorithm for solving systems of linear equations by making use of an augmented matrix and elementary row operations. So we're going to make the process that we looked at in section 1.1 a little bit more precise in this section by defining some new forms for rectangular matrices. So let's start by introducing some terminology. So we'll start with a few definitions. So throughout this section and the remainder of the course, we would define a non-zero row or a non-zero column of a matrix to be any row or column that contains at least one non-zero entry. So that is a non-zero row or column is any row or column of a matrix that does not consist of all zeros. Now, for a non-zero row, we can define what's called a leading entry of that row to be the first, and when I say first, I mean leftmost. If we're reading the entries of a row from left to right, the first entry would refer to the leftmost entry. So a leading entry is the first non-zero entry in a non-zero row. So if you're looking at the rows of a matrix, the first, for any row, the first non-zero number that appears in that row is called the leading entry of that row. Now, a couple of forms for matrices that we're going to be considering throughout this section are the so-called echelon forms. So we would say that a matrix is said to be an echelon form, or sometimes called row echelon form, if it has the following three properties. So the first property is that all non-zero rows are above any rows of all zeros. So if we're looking at a matrix where all the non-zero rows appear above the rows consisting of all zeros, that is the first property that we have for echelon form. The second property is that each leading entry of a row is in a column to the right of the leading entry of the row appearing before it. So that condition seems a little bit messy when you read through it in words, but when we start looking at some examples, we'll look at what exactly that condition means when we look at the rows or columns of our matrix and see that it's not quite so bad. And then the third condition that we have to have for echelon form is that all entries in a column below a leading entry are zeros. So for any column in a matrix that is in echelon form, the entries that appear below a leading entry need to be all zeros. So as an example of this, let's consider one of the matrices that I've written a little bit below this. As an example of an echelon form matrix, let's look at this matrix A. So let's see that it does satisfy all three conditions for an echelon form. So the first condition was all non-zero rows are above any rows of all zeros. And as we can see by looking at the rows of A, well, it doesn't have any zero rows. So it automatically satisfies our first condition. We're told that each leading entry of a row is in a column to the right of the leading entry of the row above it. So let's look at, for each row, what our leading entries are. Recall that a leading entry is the first non-zero number that appears in that row. So for our first row, the first non-zero entry is this number 2. That would be the leading entry of the first row. For our second row, the first non-zero entry is this number 1. So that would be the leading entry of our second row. And for our third row, the first non-zero entry is this number 3. That would be the leading entry of our third row. So we see the way that these rows are organized, that each of these leading entries in a row is in a column to the right of the leading entry of the row before it. That is, our leading entries are sort of proceeding from top left corner of our matrix downward to the right. So in our, for instance, the leading entry in our second row was in a column to the right of the leading entry of our first row. And the leading entry of our third row was in a column to the right of the leading entry for the second row. So it satisfies condition 2 as well. And the third condition for echelon form is that all entries in a column below a leading entry have to be zeros. So if we think about the leading entry in our first row, we had a leading entry of 2, and we see that all of the entries below 2 in that first column are 0. The leading entry in our second row was 1, and we can see that all entries below that in the second column are 0. And our leading entry for the third row was 3. There are no rows below it, therefore we could say, well, all entries below it are 0 since there are no rows below it. So it satisfies the third condition as well. So this matrix A is in echelon form, or row echelon form, and we can introduce another definition here. We would say that if a matrix is in echelon form and it also satisfies the following additional conditions, then it is said to be in reduced echelon form, or sometimes called reduced row echelon form. So to be in reduced echelon form, we have to have a matrix which is in echelon form, and additionally, these conditions 4 and 5 hold. So let's look at these. Condition 4 is that the leading entry in each non-zero row must be 1. And the fifth condition is that each leading 1 is the only non-zero entry within its column. As an example, let's see whether our matrix A satisfies these 2 additional conditions. So looking at condition 4, the leading entry in each non-zero row is supposed to be 1. So we can see right away from our first row of the matrix A that leading entry is not 1. Therefore, the matrix A is not in reduced row echelon form. It was echelon form, but not reduced echelon form. So let's look at an example of a matrix that would be in reduced echelon form. So as an example here, I'm giving the matrix B. So let's check that it satisfies these conditions. So the first condition we had to check was all non-zero rows are above any rows of all zeros. And we see, well, since B doesn't contain any rows of all zeros, it automatically satisfies our condition number 1. The next condition was that the leading entry of each row is in a column to the right of the leading entry of the row above it. So for our first row, our leading entry was this 1. For our second row, the leading entry was 1. And for our third row, this leading entry was also 1. And we see that the leading entry in the rows that appear below our first row are in a column to the right of the leading entry of that previous row. So it sort of has what's called this staircase pattern. If our leading entries have sort of this staircase form when we look at our matrix. So it satisfies the second condition. The third condition is that all entries in a column below a leading entry are zeros. So for our top left, or for the leading entry in our first row, which was 1, we see that all of the entries below it are 0. For our leading entry in the second row, we have all zeros below that. And for our last row, well, it doesn't have any rows below it, so we can say that any entry which would appear below that third row would be a 0, since there are no entries below the third row. So B is a matrix which is in echelon form. Now let's see if it is also in reduced echelon form. So condition 4 is that the leading entry in each non-zero row has to be 1, which it was. We checked that when we identified our leading entries. In each row, the first non-zero entry is a 1. And the last condition is that the leading entry of 1 is the only non-zero entry in that column. So for our first column, this leading entry of 1 is the only, let me change colors here, 1 in this first column is the only non-zero entry in that column. For our second row, the leading entry of 1 is the only non-zero entry in that second column. And for our third column, or our third row, the leading entry 1 is the only non-zero entry in that third column. So it does indeed satisfy the fifth condition for being in reduced row echelon form. So here, the matrix B is said to be in reduced row echelon form. And matrices which are either in echelon form or reduced echelon form are referred to as echelon matrices or reduced echelon matrices. All right. So here we've seen a couple of examples of matrices that are in either echelon form or reduced echelon form. So let's look at maybe a little bit more general case or general example of an echelon matrix or a reduced echelon matrix. So here I'll say the following matrix is in row echelon form. Let's make our example a little more general here. So maybe we'll call this matrix A. So we see that our leading entries, which are denoted in general as these little squares within our matrix, can have any non-zero value. And we see that these leading entries in each row, that is the first non-zero entry in our row, sort of forms this staircase or step pattern. So here every leading entry is in a column to the right of the leading entry in the row before it, because it does form this sort of staircase pattern. And the entries that are marked by stars or asterisks within this general matrix can have any value. So any real numbers for these entries that are marked by stars. Now notice that all of the entries below this so-called staircase line, that is the entries below each of our leading entries, are zeros, which needs to be true for our third condition for an echelon matrix. So a little more general, we could define an echelon matrix in this way. So one way to identify an echelon matrix is by making sure that each step of our staircase only has height 1, so that we don't have any zero rows appearing before non-zero rows, and then make sure that we have zeros below that staircase line. So these other entries which I'm marking within our matrix, let's show here these circled entries, that is an asterisk inside of a star shown here or here, would be entries or entries in a column that do not have a leading entry. And what we're going to see throughout this section is if we're using this matrix as the augmented matrix for a linear system, those columns will be used for variables that will correspond to free variables. That is, I'm free to choose those variables however I want. So as a little more general example of a reduced echelon matrix, let's consider the following matrix B. So here, this is in reduced row echelon form. Notice that each of the leading entries in our row is a 1. And so we have this staircase pattern for our matrix. The height of each step is 1. And we see that we've got all zeros below that staircase line. So we have a matrix which is in echelon form. Now, to make sure that it is in reduced echelon form, well, we need to make sure each of our leading entries is a 1. So here we can see directly from our matrix that these leading entries are all 1s. And all of the entries above and below each of these leading ones is 0. That is, the leading entry 1 is the only non-zero entry in a given column. So for our first leading 1, we have zeros below it. For our next leading entry 1, we have zeros above and below it. For this one, we have all zeros in that column. For this one, we have all zeros in the column. And for this leading one, we have all zeros in that column. So again, for any leading one, we have to have zeros above and below that leading entry to be in reduced echelon form. And again, here in this general example, the star entries can denote any number, and these star entries which have been circled define columns of our matrix that do not have a leading entry of 1, and these will correspond to free variables if we think about a system which has this as its augmented matrix. So now that we've looked at what it means for a matrix to be in echelon or reduced echelon form, let's look at the following example. So in this example, I will give you a matrix and you have to determine whether it is in row echelon form, reduced row echelon form, or neither. So in part A, we have the following matrix. So let's look at our leading entries here. For the first row, we have a 1 as our leading entry. For the second row, we have a 1 as our leading entry. Our third row is all zeros, so it does not have a leading entry. And our fourth row has a leading entry of 1. So notice here, if we're forming this staircase pattern connecting our leading entries, one of our steps, namely this last step, has a height of more than 1. So this matrix is not in echelon form. So what specific property did it not follow? Well, we have here a third row that consists of all zeros, which is appearing before our last row, which was a non-zero row. So it fails the first condition for an echelon matrix. So here we would say that this matrix is neither in echelon form nor a reduced echelon form. And the reasoning is since a row of zeros appears above a non-zero row. All right. So let's look at our next one. In part B, let's look at the leading entries of our matrix. In our first row, we have a leading entry of 1. In our second row, we have a leading entry of 2. Third row, leading entry of 3. In our fourth row, 4. So we have this staircase pattern where the height of each stair is indeed 1. So we have all of our non-zero rows listed before any rows of 0, so it satisfies the first condition. The leading entry in each row is in a column to the right of the leading entry in the row above it because it forms this staircase pattern. And we see here that for each of our leading entries, 1, 2, 3, or 4, the entries below those leading entries in each column are zeros. So this is in echelon form. So let's start by saying that this matrix is in echelon form. Now the question is it in reduced echelon form? And we can see here pretty quickly that it is not. One reason that this is not in reduced echelon form is that we have leading entries which are not 1. Recall, for reduced echelon form, each leading entry has to be 1. So this is in echelon form, but not reduced echelon form. And the reason here is since we have leading entries other than 1. All right. Now in our last example, part C, we have the following matrix. So let's take a look at this. In our first row, our leading entry is 1. Second row, leading entry is 1. And third row, leading entry is 1. So we do have this desired staircase pattern with a step height of 1. The entries below that staircase are all zeros, so the entries below each leading entry are 0. And we see that each leading entry appears in a column to the right of the column or of the leading entry in the row above it. So it is in echelon form. Now the question is it in reduced echelon form? So here we see that each of our leading entries is indeed 1. So it satisfies that condition number 4. And then for each of these leading entries of 1, we see that we have all zeros in the columns which contain those leading entries. So this matrix satisfies all 5 conditions. So this is a matrix which is in reduced echelon form. All right. So here, problem in identifying matrices which are either in reduced echelon form or simply in echelon form, or maybe neither. So we will see, or we have seen a little bit already in our first section, 1.1, that any matrix which is not all zeros, so any matrix consisting of elements which are not all 0, can be transformed into echelon form or reduced echelon form by performing elementary row operations. Those are the 3 operations that we saw in section 1.1. So interchanging 2 rows, multiplying any row by a non-zero scalar, or adding or subtracting scalar multiples of one row from another. Now this process of forcing a matrix to be in either echelon form or reduced echelon form is called row reduction of that matrix. And what we will find, we'll see pretty easily from our next example, is that any non-zero matrix can be transformed into several different echelon forms. In fact, infinitely many different echelon forms. But if we transform a given matrix into a reduced echelon form, then that form is unique for that matrix. So we have the following result of uniqueness of the reduced echelon form of a matrix. So formally, what this theorem says is that any non-zero matrix is row equivalent to one and only one reduced echelon matrix. Now there are several different echelon matrices which are row equivalent to a given matrix, but there is only one reduced echelon matrix, which is equivalent to a given non-zero matrix. Now, when we perform this process of row reduction, we're going to be making use of something called pivots or pivot columns of a matrix. So let's introduce a little terminology before we look at an example of row reduction. So here we would say that a pivot position of a matrix A is a location or an entry in A that corresponds to a leading 1 in the reduced echelon form of that matrix. And a pivot column is a column of the matrix A that contains a pivot position. So any column containing a pivot position is called a pivot column. And a pivot is any non-zero number in a pivot position that is used to create zeros via row operations. So here we've worked with pivots a little bit already. It's any pivot, any number in a pivot position that we use to kill off constants in rows above or below that pivot. So as an example, let's look at the following. So here we are given a matrix A, which is clearly not in echelon form, nor reduced echelon form. And we are asked to row reduce this matrix to reduced echelon form, and then circle the pivot positions in the final matrix and our original matrix, and list our pivot columns. So here, let's start by rewriting our matrix below so that we can perform some row operations on it. So our first row here was 1, 3, 5, 7. Second row was 3, 5, 7, 9. Third row was 5, 7, 9, 1. So we want to try to force this matrix to be in reduced echelon form. And usually the way that we proceed is moving column by column. So in our first row, this leading position was 1. And we're going to use that coefficient of 1 to kill off the constant of 3 and 5 below it. We know to get down to reduced echelon form, that leading 1 has to be the only non-zero entry in that column. So to kill off the constant 3 in our second row, we could take row 2 and subtract from it 3 times our first row. So my first row I'm going to leave alone. I have 1, 3, 5, 7. My second row, when I perform this operation, well, I have a -3 plus 3 gives me 0. For my second column, -9 plus 5 is -4. -15 plus 7 leaves me with -8. And then -21 plus 9 leaves me with a -12. And then in our third row, to kill off that leading 5, I could take row 3 and subtract from it 5 times my first row. So that makes my third row 0, -8, -16, and -34 when we perform this operation. So now my first column looks exactly like what I want. I have a 1 for the lead position in the first row and zeros below it. So now let's move to our second column. So moving downward, our leading position in the second row is this -4. And I know that I want to have a 1 there to get this into reduced echelon form. Now notice that in this example, our second row consists of entries which are all multiples of 4. So if I wanted to get a positive 1 for the leading entry in that second row, I could simply take my second row and divide through by -4, or take -1/4 of my second row. So let's see what this gives us. Our first row is still 1, 3, 5, 7. Our second row, dividing through by -4, becomes 0, 1, 2, 3. Now, in our last row, we could simplify a little bit by noticing that each of our entries in this last row is even. They're all divisible by 2. So to simplify my third row a little bit, well, I could take my third row and divide through by -2, or take -1/2 of the third row, and that makes my third row 0, 4, 8, 17. So now my matrix is getting a little closer. I have 1s for the leading entries in my first and second row. Now in that second column, I want this leading entry of 1 to be the only non-zero entry. So I need to kill off the 3 above it and the 4 below it. So let's see how we could do this. To kill off the 3 above that 1 position, I could take my first row and subtract from it 3 times the second row. So I'm using that leading entry of 1 in the second row as a pivot. I'm using it to get 0 entries above and below that entry. So performing this operation, my first row reduces to 1, 0, -6 plus 5 is -1, and then let's see, we have -9 plus 7 is -2. Now my second row I'm going to leave alone for now. We have 0, 1, 2, 3. And in my third row, I want to kill off that constant of 4. So to do that, using the leading 1 above it, I could take row 3 and subtract 4 times row 2. So that would give me a last row of 0. -4 plus 4 becomes 0. We have -8 plus 8 gives me 0. And in our last column, we have -12 plus 17 leaves me with a 5. So now for my first 2 rows, I have a leading entry of 1, and I've got zeros above and below that leading entry for each of those first 2 rows. Now in my last row, my leading entry is a 5, and I want it to be a 1. Remember, for reduced echelon form, we need to have a 1 for the leading entry in each row. So an easy way to get a 1 in that last row would be to take 1/5 of the third row. Just divide the third row through by 5. So my first 2 rows are the same. I have 1, 0, -1, -2, 0, 1, 2, 3. And dividing the last row through by 5 gives me the leading entry of 1 that I wanted in that last row. Now, to get this, or the last step to get this into reduced echelon form is that for this leading 1 in my third row, I need to have zeros everywhere above and below it. That is, I need to kill off this -2 and +3 that appeared above that last 1 entry. So to kill off the -2 in my first row, I could take row 1 plus twice row 3, which gives me a first row of 1, 0, -1, 0. For the 3 appearing in the last column of my second row, to kill that off using the leading 1 in my third row, I could take row 2 and subtract from it 3 times row 3. So that would give me a second row of 0, 1, 2, 0, and my last row is 0, 0, 0, 1. So at this stage, we have a matrix whose leading entries are all 1. we have 0 entries above and below 1 in each column. And each of these leading entries is in a column to the right of the leading entry of the row above it. So this matrix is in reduced echelon form. So the matrix that we were looking for our final answer here is this matrix 1, 0, negative 1, 0, 0, 1, 2, 0, and 0, 0, 0, 1. So this would be the matrix that we were given A, reduced to echelon form. Reduced echelon form. Now we were also asked here to circle the pivot positions in our final matrix and in the original matrix and list our pivot columns. So here, the pivot positions in our final matrix were the positions corresponding to 1s once we get it in reduced echelon form. So these leading entries 1 were the following positions, and the corresponding pivot positions in the initial matrix would be the entries corresponding to those pivot positions. So that is 1, 5, and 1 here. Now, lastly, we're supposed to list our pivot columns. So we see which columns have these pivot positions, and we see that we have pivot positions in our first column, second column, and fourth column. So here we would say that the pivot columns are columns 1, 2, and 4. All right. So we could generalize this process by performing these types of row operations, and it can be established. It's difficult to prove. I don't think they even give the proof of that uniqueness theorem in your text, but it can be shown that any non-zero matrix can be placed in echelon form by following this row reduction process, making use of elementary row operations. And any matrix is row equivalent to a unique reduced echelon matrix. So let's look at some applications here. So we've actually already seen some applications of this row reduction algorithm when we were solving linear systems in section 1.1. We just didn't have the terminology of a echelon matrix or a reduced echelon matrix. But the process that we were using in section 1.1 to solve linear systems is the following process or algorithm. So in general, to solve a linear system, we want to express that system in terms of an augmented matrix. So we saw how to do that in section 1.1. And then we're wanting to perform row reduction on that augmented matrix to convert it to echelon form, or more ideally, reduced echelon form. And once we have our matrix in reduced echelon form, we can obtain our solution pretty easily. All right. So let's look at an example of this. In this next example, we are asked to find the general solution of the following system. So here we have a system of 2 linear equations in 3 variables, x1, x2, x3. Now in our first section, 1.1, we were only working with systems that had the same number of equations as variables. In this example, we see for the first time a system of only 2 equations in terms of 3 variables. So this type of system is what is sometimes referred to as an underdetermined system. That is a system with fewer equations than variables. So here, 2 equations, but 3 variables makes this what we would call an underdetermined system. So let's think about how to solve this system. So in general, our process for solving a linear system is to express this as an augmented matrix. So here, the first row of our augmented matrix would be 1, -2, -1, and 3, where I'm going to put a vertical bar in my matrix to denote a equal sign, or to denote which coefficients are coefficients of my variables and which entry represents a constant on the right-hand side of my equation. Now my second row in the matrix would be 3, -6, -2, 2. So our goal here is to reduce or transform this matrix into reduced echelon form, and from that point I can obtain my solution. So here, let's see what we want to do to row reduce this. In our first row, we have a leading entry of 1, and I know to get it in reduced echelon form, I need to kill off the entry of 3 that appears below it. So one way that I could accomplish that would be to take my second row and subtract from it 3 times the first row. So my first row remains the same. I have 1, -2, -1, 3. And my second row, when I perform this operation, reduces to, let's see, we've got -3 plus 3 is 0, +6 minus 6 is 0, and then a +3 minus 2 leaves me with 1, and then performing the same operation on the right-hand side of our equation, we have a -9 plus 2 leaves me a -7. So I now have a 1 for both leading entries in this matrix. For my first leading entry, or the leading entry in the first row, I've got zeros everywhere above and below that entry. So to put this in reduced echelon form, well, I just need to kill off the -1 that appears above my leading 1 in the third column. So an easy way to do that here would be to take my first row and add to it the second row, which gives me a first row of 1, -2, 0, and -4. And my second row is 0, 0, 1, -7. So here we had leading entries or pivot positions corresponding to these 2 entries. So here we have 2 equations relating 3 variables, and when we have this sort of system, we would have infinitely many solutions, I claim. Now, how do we know infinitely many? In the first section, 1.1, we said, well, we would have infinitely many solutions and make use of a free variable anytime that we had a row of all zeros in our augmented matrix. Now here, we only have 2 equations in 3 variables. So our coefficient matrix is a 2 by 3 matrix here. But if we were to think about that matrix as being square, well, we could impose a third equation of just 0 equals to 0, the trivial equation, as a third row, in which case we're going to make use of a free variable. Now, when we're using this row reduction algorithm and we have a matrix in reduced echelon form, the free variables are going to correspond to the columns which do not have leading entries, or non-pivot columns. So here we had seen that our pivot columns were the first column, which has elements corresponding to the variable x1, and x in our third column was a pivot column, which has coefficients corresponding to x3. So this entry that we have here of -2 is a non-pivot column, which will correspond to a coefficient of a variable x2. And so here we're going to let x2 be our free variable. So let's see what we have here. We will let x2 be a free variable. Or if you want to make a specific choice for x2, you could take x2 to be some real number t and call that a free variable. Now, if I know what x2 is, I'm allowed to choose it as any real number that I want. I still need to find x1 and x3. So let's think about how to find x1. Looking at the first row of my augmented matrix, if I write this out as an equation, it says 1x1 minus 2 times x2 plus 0x3 has to equal -4. So solving for x1, I have x1 is 2 times x2 minus 4, or if I prefer 2t minus 4. And I still need x3. Now to get x3, we can look at our second row of our augmented matrix in reduced echelon form. And that second row says 1x3 is equal to -7. So I have -7 right away. So here my solution set would be the set of all points x1, x2, x3, where x1 is given by 2t minus 4, x2 is equal to t, or x3 is equal to -7, such that t could be any real number. So here we have infinitely many solutions, and in fact, most of the time when we're working with underdetermined systems, we will have infinitely many solutions. More often than not, when we have fewer equations than variables, one of our variables will be free. So here, this underdetermined system has infinitely many solutions, which are of the following form. All right, so let's look at another example. In our next example, we have the same sort of problem that we were considering previously, but we're already given the augmented matrix. So here we are asked to find the general solution of the system whose augmented matrix is given by the following. Now recall here that in my notes I'm using the same notation as your textbook where they omit the vertical bar in the augmented matrix. In my own work, I personally prefer to put a bar before that last column so that I know where the equal sign is within my equations. So let's see if we can find our general solution here. So I want to row reduce the given matrix to be in reduced echelon form. So looking at it here, well, my leading entry in the first row is a 1. In my second row, we have a 1. And in my third row, I've got a -1. And I know I want to try to kill off that -1 in the third row so that the only non-zero entry in my first column is that leading 1. So an easy way to do that here would be to simply add row 1 to row 3. So my first row I'm going to leave alone. I have 1, -7, 0, 6, 5. And my second row I'm leaving alone. I've got 0, 0, 1, -2, -3. And then adding that first row to my third row, I get a 0, 0, -4, 8, and 12. All right. So now my leading entry in the first row is 1. I have zeros everywhere above and below it. My leading entry in the second row is 1. I have a 0 above that entry, but I need to kill off the -4 that appears below it. So an easy way to do that would be to take row 3 and add to it 4 times row 2. So my first row remains the same. 1, -7, 0, 6, 5. My second row remains the same. 0, 0, 1, -2, -3. And my third row becomes 0, 0. 4 minus 4 gives me 0. -8 plus 8 will give me 0. And then we have a -12 plus 12 gives me 0. So here we have a row of all zeros in my final row. And let's see if this is now in reduced echelon form. We have leading entries of 1. My row of all zeros appears below every non-zero row. So that is, we have this sort of staircase pattern here. And the leading ones in each row have zeros everywhere above and below it. So if we think about this augmented matrix as representing a linear system, the entries in my first column are the coefficients of a variable x1. The entries in my second column are the coefficients of some variable x2. For the third column, x3, fourth column, x4, and then we have some constant values on my right-hand side. So here we have a augmented matrix, which is 3 by 4. So I have 3 linear equations in 4 variables. Again, this would refer to an underdetermined system. And following the same sort of process that we did in our previous example, any column which has which is not a pivot column will have this entry behind that leading entry as corresponding to a free variable. So in this example, I have 2 such columns. So I actually have 2 free variables in this example, namely x2 and x4. So here, let us take x2 and x4. We will take them to be free variables. Or if we want to choose a specific value for each variable, we could maybe take x2 to be s and x4 to be t if we want to use specific choices for x2 and x4. But these are free variables. And we still need to solve for x1 and x3. So let's look at our first equation. Our first equation says 1, or our first row of this matrix in equation form says 1x1 minus 7x2 plus 6x4 is equal to 5. So solving for x1 in terms of the free variables, we have 7x2 minus 6x4 plus 5. And to solve for x3 in terms of my free variables, I'm going to make use of my second row in the matrix, which as an equation says 1x3 minus 2x4 is equal to -3. Or x3 is equal to 2 times x4 plus 3. So once I've solved for all of my variables, I can write out my solution set. So here, our solution set is the set of ordered pairs x1, x2, x3, x4, where x1 was given by 7x2 minus 6x4 plus 5, or you can use s in t instead of x2 and x4 if you prefer. X2 was a free variable. X3 was defined as 2 times x4 plus 3, and x4 was a free variable. So it's the set of points of this form such that x2 and x4 are allowed to be any real numbers that we want, since they were free variables. Okay, so again here we're seeing an example of an underdetermined system for which we have infinitely many solutions. It's not always the case, but in a lot of cases we will have infinitely many solutions for such systems. Okay, so let's look at another one. So in the last part of our section here, before we look at some other examples, we can start to see that expressing a linear system in terms of an augmented matrix will also allow us to determine whether the system is consistent or inconsistent. That is, whether a solution even exists. So we have the following theorem regarding the existence and uniqueness of a solution of a linear system. And here's what it says. A linear system is consistent, that is, it has a solution if and only if there is no leading entry in the rightmost column of the augmented matrix after it is expressed in row echelon form. That is, if and only if an echelon form of the augmented matrix has no row of the following form, something of the form 0, 0, 0, 0, B, where B is non-zero. And let's think about why such a row in our augmented matrix would make our system inconsistent. If we think about that row in an augmented matrix by maybe using our bar notation that we've been using, that equation would say 0 is equal to B, but B is a non-zero number. So we saw examples in section 1.1 where maybe one of our equations reduced to 0 has to equal 2, or 0 equals some other non-zero constant, which is not possible, and that makes our system inconsistent. So this theorem says, in fact, the only way that a system is inconsistent is if it has such a row, or equivalently, any linear system is consistent provided that it does not have a row of that form. So we can make use of this theorem to determine when a given system will have a solution or not. So let's look at some examples of this. In this next one, we are asked to find the value or values of H such that the matrix that we're given here is the augmented matrix of a consistent linear system. So again, maybe my first step here would be to change the notation that's given in the book slightly so that I make use of this vertical bar to denote an equals within my system of two equations. So here we want to know what should the value of this constant h be in that bottom right entry in order for this system to be consistent, for a solution to exist. So to determine that, well, we can look at our augmented matrix, 1, -3, -2, 5h, -7, and I want to put it into row echelon form. I know that I have a consistent system if when I express that augmented matrix in row echelon form, I do not have any row of this form listed in our theorem. So to put this in row echelon form, well, my leading entry in the first row is 1, and I need to kill off the entry 5 that appears below that. So an easy way to do this would be to take row 2 and subtract 5 times my first row. So my first row is still 1, -3, -2. And when I perform this operation on my second row, I have -5 plus 5 is 0, 15 plus h, or h plus 15. And then let's see, we've got 10 minus 7 is equal to 3. So in order for this system to be consistent, this last row that I'm working with cannot be of the form all 0 entries equals a non-zero constant, 3. So as long as this bottom right entry is not equal to 0, then I know my system is consistent. So let's say the following. This system is consistent if and only if our bottom right entry, h plus 15, once we've expressed it in echelon form, is something other than 0. That is, if h is some number other than -15. So we can choose any value of h other than -15, and our system will be consistent here. All right. So let's look at another example. In our last one, we have a problem which is very similar to some of your 1.2 homework problems. And we are asked to choose values of constants h and k such that the system, which we're given below here, has either A, no solution, that is, it's inconsistent, B, a unique solution, that is, it has only one solution, and C, that it has infinitely many solutions. So let's take a look at this. In part A, we want to know what would the values of these constants h and k have to be to have no solution. So making use of the theorem that we just looked at, we would want to express this as an augmented matrix, where here we have a first row of 1, 3, 2, and our second row would be 3, h, k. And I want to row reduce this to row echelon form. So here, our leading entry in the first row is already 1. I need to kill off the 3 that appears below it. So an easy way to do that here would be to take row 2 and subtract from it 3 times my first row, leaving me 1, 3, 2 for my first row. And for my second row, I would have 0, h minus 9, and let's see, k minus 6. So our theorem regarding existence and uniqueness of solutions gives us a condition for when we would have no solution. So what is that condition? We would have no solution if our row, this last row of our matrix in row echelon form, would be of the form 0, 0 is equal to some non-zero number. So that would happen if this h minus 9 entry is equal to 0, and my constant k minus 6 is something other than 0. Or equivalently, if h is equal to 9 and k is not equal to 6. So this would be the condition on those constants, h and k, which would make this system inconsistent. Now in part B, we are asked what are the values of h and k, where we would have a unique solution. That is only one solution, which means that we should not have any free variables. So let's think about this. So we need to have a unique solution. So we will have a unique solution if, well, first off, a solution better exists. So my last row can't be of the form 0, 0, b, some non-zero constant. So I have to have that bottom right entry in my echelon matrix be something other than 0. So I need h minus 9 to be non-zero. And then as long as that bottom right entry is something other than 0, it doesn't matter what this constant on the right-hand side of our equation is. We could always solve the system regardless of what the constant on our right-hand side is. So here, we could say that k minus 6 could be any real number that we want. So that is, we have a unique solution if h is some constant other than 9, and k, well, if k minus 6 could be any real number, then k could be any real number plus 6, which could then be any real number. So as long as h is not equal to 9, and k is any number we want, we will have a unique solution of that system. Now in the last part of this problem, we're asked for the case where we have many solutions. Now the only way that we can have many solutions is if we're introducing a free variable. And so for our system here, which is consisting of two equations in two variables, x1 and x2, we only have a free variable if my last row is all zeros. That's the only way that I would have a column which is not a pivot column, is if this bottom right entry, my lead entry, were also 0. So here we will have, let's say, many solutions if h minus 9 is equal to 0 and k minus 6 is equal to 0. That is, if h is equal to 9 and k is equal to 6. So there's only one choice of my constants h and k, which will give me infinitely many solutions. So this finishes our section 1.2 material on row reduction and echelon forms. And this sort of ties together what we had already started to see in section 1.1 when we were using Gaussian elimination to solve linear systems. In general, to solve a linear system, our goal is to express it as an augmented matrix, as we did in section 1.1. And then we want to use our elementary row operations from section 1.1 to transform our matrix into reduced row echelon form. And once we have it in reduced row echelon form, we immediately have our solution to that system based on the form of that reduced row echelon form matrix. So moving forward in this section, we'll start, or this chapter, we'll start talking about some vector operations and other relations between solutions of linear systems and vectors or columns of